Hello everyone, welcome to our presentation on the invisible force, how electromagnetism powers modern medicine. We are group AS1203H from Physics 150. Today, we will explore how fundamental principles of electricity and magnetism enable technologies that save lives every day. So let's go. Here is our roadmap. We will start with key historical discoveries that examine three revolutionary technologies, which is X-ray for seeing bones, MRI for soft tissue imaging, and TMS for brain therapy. We will compare their electromagnetism principles and conclude with future innovations. Medical electromagnetism didn't begin in hospitals or lecture halls. It began with accidents, curiosity, and scientists daring to ask what if. In 1895, Wilhelm Röntgen was experimenting with cathode rays when he noticed something strange. A fluorescent screen glowing even though it was shielded. He had unknowingly discovered X-rays, mysterious rays capable of passing through flesh while leaving bones clearly visible. This accidental breakthrough shocked the scientific world and forever changed medicine, allowing doctors to look inside the human body without making a single incision. Decades later, curiosity once again pushed physics forward. In 1930s, physicists such as Isidore Rabi explored how atomic nuclei behave in magnetic fields, leading to the discovery of nuclear magnetic resonance, or short form for NMR. At first, this was purely a physics experiment with no medical purpose in mind. However, by 1970s, this same principle evolved into magnetic resonance imaging, which is MRI, a powerful, non-invasive tool that could produce incredibly detailed image of soft tissues, something X-rays struggled to achieve. This story didn't stop there. In 1985, Anthony Barker applied Michael Faraday's principle of electromagnetic induction in a bold new way. By using rapidly changing magnetic fields, he created the first transcranial magnetic stimulation (TMS) device capable of stimulating the human brain without surgery. What began as an electromagnetic experiment soon became a valuable clinical tool for studying brain function and treating neurological and psychiatric conditions. Together, this breakthrough showed a fascinating pattern. Ideas born in physics laboratories, often by chance, slowly transform into life-saving medical technologies. Medical electromagnetism is a proof that curiosity-driven experiments can end up changing how we diagnose, treat, and understand the human body. I will pass to my friends for further explanation.
Hi guys, I am Muhammad Izni Najmuddin bin Zahid. So let's begin with X-ray, our first case study. X-rays are high-frequency electromagnetic wave, which means they carry high energy. This relationship can be explained using the equations E equals to HF, where energy increases as frequency increases. In an X-ray tube, electrons are accelerated at very high speeds using a high voltage. These fast-moving electrons collide with a metal target, usually made of tungsten, producing high-energy X-ray photons. When X-rays pass through the human body, different tissues interact with the radiation in different ways. Soft tissues such as muscles and organs allow most of the X-rays to pass through, while dense structures such as bones absorb more of the radiation. This difference in absorption creates contrast in the X-ray image, allowing bones to appear white and soft tissues to appear darker, which helps in identifying internal structures. Clinically, X-rays are widely used to detect bone fractures, lung conditions such as pneumonia, and dental problems. One major advantage of X-rays is that they can produce images quickly and clearly, which is especially important in emergency situations. However, X-rays are a form of ionizing radiation, meaning they have enough energy to damage DNA if exposure is too high or repeated frequently. Because of this risk, medical imaging follows the ALARA principle, which stands for as low as reasonably achievable. This principle focuses on minimizing radiation exposure by using the lowest possible dose, limiting the exposure time, and avoiding unnecessary repeat scans while still obtaining clear diagnostic images. Therefore, ALARA highlights the importance of balancing medical benefit with patient safety in clinical practice.
Hi, my name is Muhammad Hazim bin Misri. In my slide, I'm going to explain about MRI, the magnetic principle. Our second technology, MRI, uses completely different EM principle. Instead of ionizing radiation, MRI employs magnets 1.5 to 3 Tesla, thousand of time Earth's field. This aligns hydrogen nuclei in water molecules. When we add radio wave at the precise Larmor frequency, omega equal to YB naught. Proton absorb energy, then re-emit it as signals we reconstruct into detailed image. My second part, I'm gonna explain about MRI in clinical power and safety. MRI's non-ionizing approach excel where X-ray cannot visualizing soft tissue like the brain, muscle, and ligaments. However, its powerful magnet creates unique safety concern. It can turn metal objects into dangerous projectiles. This technology shows how we have moved from simple absorption imaging to sophisticated signal detection from within the body itself. My last part, I'm gonna explain about TMS, electromagnetic induction therapy. Our third case, shift from diagnosis to treatment. Transcranial magnetic stimulation applies Faraday's law of induction directly, which is epsilon equal minus dV sub B over dt. A rapidly changing current in a coil creates a changing magnetic field that induces an electric field in the brain. Unlike MRI's static field, TMS use precisely timed pulses to modulate specific neural circuits.
Assalamualaikum and hi guys, I'm Muhammad Irfan and I'm going to explain about clinical application and protocol. Clinically, TMS targets the left dorsolateral prefrontal cortex, underactive in depression. According to our research article, the FDA protocol involves 20 to 30 daily sessions. Unlike electroconclusive therapy, TMS requires no anesthesia and has minimal side effects. Research now explores TMS for pains, migraines, and rehabilitation. Next, I'm going to explain about the future direction and innovation. Where is this field heading? Researchers now are developing portable or low-field MRI for emergency settings. Theta-burst TMS delivers treatment in just 3 minutes instead of 30 minutes. AI integration is enhancing image analysis and personalizing TMS targets. What is the common thread? Deeper understanding of electromagnetism enables more precise, accessible, and personalized medical technologies. Last but not least, I'm going to explain about the comparative analysis. This comparison between X-ray, MRI, and TMS synthesizes our analysis. X-rays use ionizing radiation for quick structural images. MRI uses strong magnetic fields and radio waves For detailed soft tissue visualization, TMS applies electromagnetic induction for therapeutic brain stimulation. Each three of these harnesses different EM properties for distinct medical purposes while requiring specific safety protocol.
In conclusion, electromagnetism enables remarkable diverse medical technologies, each with distinct physical principle and safety consideration, all built on historical discoveries that continue to evolve, improving how we diagnose, understand, and treat human illness. Thank you.